Envision the Arctic Ocean at the height of winter, not a drop of liquid in sight, just an endless white desert of compressed ice stretching farther than any horizon. This isn't slush, it's a concrete-like lid, several stories thick, locked together across 1,000 miles of frozen ocean. Now imagine a steel vessel, 30,000 tons of machinery, steering directly into that barrier. No hesitation, no detour. It plunges forward and somehow emerges on the other side, leaving a slick black scar of open seawater in its wake. So what's actually happening here? Is the ship simply stronger than the ice? Does the bow function like a giant guillotine blade? And how does the hull survive this abuse all winter without ripping apart? The truth flips everything you think you know. That ship isn't smashing through anything. It's performing a much stranger trick, and once you grasp it, you'll never view these vessels the same way again. Let's clear up a common misconception. Most of us imagine an icebreaker as a battering ram, a sharp, heavy point slamming into the ice edge, punching through by raw impact. That mental picture makes sense. It's also completely wrong. A 10-foot thick ice sheet is incredibly resilient when you strike its edge head-on. Hitting it like that is comparable to punching a concrete wall. The ice barely registers the blow. The ship loses that exchange. So how does an icebreaker succeed? It doesn't attack the ice from the side. It attacks from above. Icebreakers don't punch, they perch. Look closely at the front of a genuine icebreaker. The bow isn't sharp and vertical like a knife. It's sloped, curved, almost like the front of a sled. That shape holds the entire secret. The vessel doesn't drive into the ice, it drives onto it. The angled bow glides over the leading edge, and the entire front of the ship physically lifts out of the water and climbs atop the frozen surface. Now the ice isn't being punched, it's being sat upon. Think about the difference between stabbing a cracker from the edge which resists versus laying it flat and pressing down with your palm. The edge holds strong, the flat surface snaps instantly. Ice behaves identically. It's tremendously strong against sideways force, but surprisingly weak against downward pressure. An icebreaker is a machine engineered entirely to exploit that single vulnerability. Let's walk through one complete braking cycle. The ship approaches the untouched ice at a slow, steady crawl just a few miles per hour. This isn't about speed. The sloped bow makes contact and begins riding upward. The reinforced forward hull slides over the ice edge, and the entire front of the vessel begins to rise. For a heartbeat, thousands of tons of bow are no longer floating, they're suspended in air, balanced on top of the ice sheet, held up only by the frozen surface beneath. And the ice cannot hold it. Gravity takes over. The full downward weight of that lifted bow crashes through the sheet. The ice fractures, and a slab the size of a parking lot breaks free and plunges underwater. Imagine dropping a loaded cement truck onto a frozen pond. That's the concentrated downward force happening at the bow of an icebreaker every few seconds. The vessel settles forward into the gap it just created. Broken slabs roll and tumble beneath the hull. The sloped bow finds the next untouched edge and begins climbing again. Climb, press, crack, settle, repeat. That's the rhythm. An icebreaker doesn't charge, it crawls. The engines aren't delivering a punch. They're just shoving that sloped bow onto the next sheet. And those engines are absolute monsters. A large nuclear icebreaker can generate over 70,000 horsepower, roughly the combined output of 500 standard cars. All of it funneled into a few massive propellers turning beneath the ice. Those propellers matter more than you might think. They're built from thick cast steel, and the blades are often designed to be unbolted and replaced individually because chunks of ice sucked under the hull will chip and crack them. The propeller wash also serves a second purpose. It blasts broken ice backward and away from the stern, helping flush the channel clear so it doesn't simply freeze shut again behind the ship. Now here's the part that defies all intuition. Sometimes the ice is simply too thick for that steady rhythm to work. Pressure ridges where two ice sheets have collided and buckled can pile up far thicker than the surrounding flow. The ship rides up, presses down, and the ice holds. So, what does the ship do? It goes backward. The icebreaker stops, reverses several ship lengths into the channel it has already cleared, then drives forward at full power to ride as far up onto the ridge as possible. Then it backs up and does it again and again. It's called backing and ramming. The strongest ships on Earth defeat the hardest ice by repeatedly retreating. It's like needing to reverse your car down the driveway just to get a running start at a snowbank. And it gets even stranger. The most powerful icebreakers are deliberately built wider than the cargo ships they escort, because the channel must be wide enough for those vessels to follow without scraping. Some modern icebreakers are even designed to break ice while traveling backward using a specially shaped stern, because in certain conditions, going in reverse clears a better path than going forward. A ship engineered to work best while moving in the wrong direction. That's how upside down this field becomes. So how does the hull survive all this without being shredded? This is where hidden engineering lives. The hull of a true icebreaker is not a normal ship's hull. Around the waterline where steel meets ice, the plating is enormously thick. We're talking steel several inches deep, layered like stacking multiple car hoods together into one solid wall. Behind that outer skin sits a second inner hull, a double wall. If the ice ever tears the outside open, the inside still keeps the ocean out. The hull is also rounded underneath, with no sharp lower edges for the ice to grab onto. This shape matters for a reason most people never consider. If an icebreaker ever gets trapped in ice, squeezing it from both sides, that rounded form means the pressure pushes the ship upward instead of crushing it inward. The vessel pops up like a wet watermelon seed shooting out from between two fingers rather than being slowly flattened. Then there's the problem of friction. Broken ice scraping along the ship's steel sides slows it dramatically. So many icebreakers carry a system that blows compressed air out through holes below the waterline, wrapping the hull in a curtain of rising bubbles. Some use jets of water instead. Either way, the ice is lubricated, so it slides past the steel instead of gripping it. The hull becomes a wet bar of soap, and the ice just slips off. Some ships go even further. They carry tanks of water on either side and pump it rapidly back and forth, deliberately rocking the entire vessel. That rolling motion widens the channel and shakes loose ice clinging to the hull. A 30,000-ton ship intentionally wobbling itself free. None of this was figured out overnight. The first real icebreakers appeared more than 100 years ago, and the sloped bow was the breakthrough that changed everything. Before that, ships just rammed the ice and hoped. Every shape you see on a modern hull was earned through decades of vessels getting stuck, getting crushed, and getting redesigned. Here's why all this matters far beyond the Arctic. You may never see an icebreaker in person, but you've almost certainly benefited from one anyway. Northern cities and remote settlements rely on ships for fuel, food, and supplies, and in winter, the sea route to reach them freezes solid. An icebreaker goes first, carving a channel, and the supply ships follow single file in the open water behind it. It's a snowplow clearing a lane on a highway so the cars behind can finally move. Frozen ports of the far north stay open through winter only because icebreakers keep grinding their channels open. Research vessels studying climate at the top of the world get their own ice-breaking holes. The natural gas and oil that flows out of Arctic terminals reached the rest of the planet on tankers that an icebreaker cleared the way for. Whole economies rest on this. The price of heating fuel in an Arctic town in February quietly includes the cost of a ship that spent days breaking a path to deliver it. But this system has a brutally honest cost. Icebreaking is painfully slow. A ship that crosses an ocean of open water in days can spend that same time crawling through a single difficult stretch of heavy ice. It's one of the most fuel-hungry jobs in all of shipping hours of straining engines to travel a distance you could walk. And it's not guaranteed to work. A ship can get beset. That's the term for being frozen in place when surrounding ice closes in and locks the vessel solid. The pressure of ice sheets driven together by wind and current can be immense. A 30,000-ton ship, one of the most powerful machines humans have ever floated, can be held completely motionless by nothing but frozen water pressing on its sides. Crews have been trapped like this for days, waiting for the wind to shift and the ice to loosen its grip. In the worst cases of the past, ships caught this way were slowly crushed and lost entirely. The ice always gets a vote. So here's where you land after all this. You started out picturing a battering ram, a ship that wins by hitting harder, brute force against a frozen wall. What's really out there is something much smarter, a machine that refuses to fight the ice on the ice's strongest terms. It climbs instead of charging. It turns its own enormous weight into a downward blade. It lifts itself up just so gravity can do the braking for free. It's not strength against the ice, it's geometry against the ice. Next time you see footage of one of these ships carving a dark path across a frozen horizon, you'll know it isn't smashing anything. It's climbing, pressing, and falling thousands of tons at a time. If this changed how you see icebreakers, hit like for Exhaust Zone and stick around.